Hello, and thanks very much for the opportunity to talk. I'm going to tell you about the work of the Quantum Communications Hub on secure communications at all distance scales. But given this audience, I'm going to focus on the largest distance scales and space quantum communications. So just a bit of quick background, just to give you the context. The Quantum Communications Hub is one of four national hubs that comprise the academic-led low TRL part of the UK National Quantum Technologies Programme. So there's a hub on sensing and timing led by Birmingham, one on imaging led by Glasgow, one on computing led by Oxford, and then I lead the Quantum Communications Hub from York. And in addition to the four hubs, there's now a National Quantum Computing Centre being built on the Harwell campus that, if you like, is a tech transfer route for the computing work. And so that's the background. The hub is part of the UK National Quantum Technologies Programme. And what we do, well, we work on quantum communications. And at the minute, I think it's fair to say that most of the quantum communications work is focused on security. That will change in the future as there's more of a convergence between computing and communications, and we see entanglement distribution and distributed processing and so on happening. But at the minute, most of our work that we do is focused on security. And so the background to this, security is clearly very important, but the background to this is that there is a potential threat in the future from quantum computing technologies that actually exposes current public key infrastructure such as RSA and elliptic curves. So Peter Shor's algorithm shows how we could, with a large quantum computer, actually break these crypto systems. And although a large quantum computer doesn't yet exist, it's been rather elegantly captured by Michele Mosca that we don't necessarily need to wait until such a quantum computer appears. But if we have interest in keeping our data secure well into the future, and it takes a while to retool hardware and software for security, then potentially we need to be worried now about the looming threat in the future, not simply when a quantum computer appears. So if you like, that's the bad news. And the good news is that new quantum communications technologies are being developed, and new mathematical cryptography, and these are being developed in parallel at the minute, and I think putting these two together in the future is the way we'll see data security evolve. I know some people like to put these as competitors, if you like, but I think it's going to be a combination of secure quantum communications technologies and new mathematical cryptography, so-called post-quantum cryptography, that we need to put together for future security. So sector perspectives, our security technologies, if you like, apply everywhere. I mean, every sector, whether it's government, commercial, or personal and consumer sectors. Security of data is relevant across all of these sectors. So perhaps that's slightly different from some other quantum technologies where there are very specific technologies that will serve particular sectors. But in our case, security applies everywhere. Now, that said, of course, it may well be that the security requirements in different sectors and the flexibility required and the distances over which they need to operate will vary from sector to sector. And so the actual solutions that will be provided will be more sector specific. So, you know, for example, clearly size, weight, and power constraints are important everywhere you go these days. But in particular for us, I would say that the size, weight, and power constraints are very important at the shortest range of free space quantum communications. That's for short range mobile, consumer-based, if you like, quantum comms, and also the very longest distances where we're going from ground to satellites. So swap constraints are particularly important in both of those scenarios. It's also the case that some, certainly in the future, some of the solutions that we will provide in secure communications will have more sector-specific application. For example, there's analogs in the quantum world of money and secure tokens and things that may be more relevant for banking. The other thing that I'd like to say, and I'll mention it again later as well, because it is very important, is that standards and assurance are very important when it comes to security. So they apply across all sectors. Standards and assurance are essential for us. So Most of what we work on at the minute is based on key distribution. So almost all of the activities that we've undertaken in our work for the UK National Quantum Technologies Programme since the beginning in 2014 has focused on quantum random number generation, but mainly quantum key distribution. These are the most mature technologies, and so we've been pushing those towards application and up the TRL stack. Key distribution in the quantum case is achieved by sending quantum signals between the two people who are always called Alice and Bob in this scenario. And if you like, you have inbuilt tamper detection built into nature. So it's not something that can be avoided. So Alice and Bob have a physical method of determining whether anyone has intercepted their signals. And if that's not the case, then they have a method for sharing a secure key. Now, once keys have been shared, they can be used for all manner of applications. It could be data encryption and decryption, but it could be for entry through a door or as a password or a passport or so on. So once you have a key, there are all manner of non-quantum ways in which you can use it. But in almost all of these scenarios, if you use a key once, you should then delete it in order to maintain the security, which means that keys are consumables. Not only do you need to establish them in the first place, but you need to refresh them at various points. And that establishment and the refresh are where quantum comes in, and the use is not quantum. The other important point to note is that authentication is an additional requirement. You don't get it from quantum key distribution. You have to input it to quantum key distribution. That can be done through pre-shared key, but if you're in a very dynamic networking situation where Alice's and Bob's are coming and leaving all of the time, then clearly having pre-shared key between everyone is not a scalable solution. And so one needs some alternative. And that's possibly where quantum security and post-quantum security will be put together in a hybrid solution. I just want to mention very briefly our work at the very shortest distances. And the reason for mentioning it is that, in fact, our development of short-range free space handheld consumer QKD systems, if you like, that's a receiver that might go in your phone and a transmitter that might go in your phone and a receiver that would sit in a device in the wall. That technology has actually underpinned our work at the other end of the spectrum for space because, as I said, low swap is very desirable for both ends of the distance spectrum for quantum communications. Now, if you go to intermediate distances, so that's around cities and between cities, certainly in a country the scale of the UK, then fiber networks are clearly what we use for ordinary communications, and we can leverage such fiber networks for quantum communications. And indeed, within the UK, we, the Quantum Communications Hub, established the UK's first quantum network. And that comprises a small trusted node QKD network around Cambridge, a similar small trusted node QKD network around Bristol, a connection from Cambridge to British Telecom's R&D headquarters at Adastral Park, and then we're borrowing bits of the National Dark Fiber facility to connect the networks in Cambridge and Bristol together. And this work has very nicely led to further developments. So we did tech transfer into industry-led projects that were funded by Innovate UK, and it's now very pleasing to see that even following on from that, British BT and Toshiba are now operating a commercial trial with EY as a customer within the City of London. So it's very interesting to see the development of that fiber-based technology work. The reason I wanted to mention it is that, in fact, if you go to larger distances still, so you want to connect between fiber networks in different countries, and particularly if that utilizes undersea fibers, then undersea fibers in general, if they contain conventional amplification, are simply not suitable for quantum key distribution because those amplifiers destroy the quantum signals. Therefore, if you want to connect over the largest distances with secure quantum communications, then going via satellites seems to be the obvious way to go. And so at the very largest distances, then satellites are the appropriate vehicle. And there is much R&D underway worldwide now investigating secure quantum communications to and from satellites. One important point to note, in the same way that actually on the ground at the minute, most of the technology is trusted node QKD, that's that you have to trust various nodes in the network. In that same way, at the moment, until satellites can support quantum memories and repeaters and deliver entanglement distribution to various places at high data rates, then the trusted nodes are satellites as well, and that's not a bad thing because that mirrors what's going on the ground. But at the minute, that limitation is what we're stuck with until we can expand space quantum communications to put memories and repeaters into space. So what are we doing in the hub? Well, in the hub, we're about to launch, well, in 2024, we plan to launch a CubeSat, a 12U CubeSat supplied by ISIS Space, and we'll be putting QKD transmission on that CubeSat, and we'll be receiving it at an optical ground station that's going to be based at Errol Airfield in Scotland. So we intend to do an in-orbit demonstration of quantum key distribution. There are other UK related missions going on at the minute. So there should be a CubeSat mission called ROX that's led by Craft Prospect in the UK, and there's also a CubeSat mission that's joint between the UK and Singapore called Spectre, and the UK lead on the Spectre project is RALSpace, and RALSpace are also our delivery partner in the hub for our CubeSat mission. So there are 3 missions due to go up with UK links in the next couple of years, and in addition to that, there are also international collaborative projects going on. So the Canadians are launching a KeySat satellite, which will contain various quantum technologies. And although the main focus of KeySat is actually an uplink, so they will fire quantum signals from the ground at KeySat, there is also going to be a downlink source on that supplied as part of a project in the UK Canada Quantum Technologies program that was launched a few years back. And in the hub, we are also using partnership resource funding that we have, exploring the possibility of an entangled source that we can use for an uplink from our ground station in the UK. So the message is there's basically a lot of activity going on at the minute in the R&D phase of exploring quantum communications in space. I just want to mention a couple of other things. I've said most of what we do is key distribution, but there are protocols being developed that go beyond key distribution, which means that we broaden out the scope of quantum communications. I think it's interesting that some of those protocols, so-called position-based cryptography class of protocols, actually bring in another physical constraint, and that is the finite travel time for information. So we have a constraint from relativity that information cannot travel faster than the speed of light, and along with the disturbance that you get when you make quantum measurements, those 2 physical constraints can be used in interesting new protocols. And of course, it's worth pointing out that relativity is also a constraint when it comes to satellite communications. So you have to make sure that reference frames are allowed for with moving satellites and so on. So, but the message is there's basically interesting stuff to come that broadens out beyond just key distribution. And clearly some of that we would like to see put in space in the future. I've already mentioned that standards are very important, but I will say it again because there's now there's now a real growth in standards activities worldwide, looking into all manner of quantum technologies, but particularly quantum communications, because they are one of the most mature quantum technologies. I also mentioned putting together, if you like, new mathematical post-quantum crypto and QKD, and NIST in the US has been leading the development of the new PQC standards, and so that process is now coming to a close. And so over the next year or 2, we expect to see work hybridizing QKD with the outcomes of the NIST process on PQC. I do also want to point out that clearly security technologies need assurance, and the National Cybersecurity Centre in the UK are the body that traditionally oversee assurance of all secure technologies that are deployed in the UK, and that's clearly a growing task given the expansion of the cyber world. And so NCSC have now evolved the way in which they provide security technology assurance. So earlier this year, they announced a whole list of standards, a whole list of principles that new security technologies need to be developed under, and then also obey during their operation. And so the way it will work in the future is that companies and service providers will have to make sure that security technologies follow all these principles and evidence that indeed they are doing so. So we are at the minute looking into the implications of this new approach to technology insurance, particularly for the quantum secure technologies. And so I want to finish off by thinking about what's next, if you like, for quantum in space with the UK. So as I pointed out, we've got 3 CubeSat missions that will be going up in the next couple of years, and we've got growing international collaboration, such as the Canadian KeySat mission. But I'm sure you're all aware now that given Brexit and so on, the EU and the European Space Agency are certainly looking to expand their activities in quantum in space. And of course, now the UK is in this position where we are excluded from various EU security R&D in the future. And so I think it's very important that the UK keeps in mind and expands our activities on quantum in space, because some of the partnerships that we might have sought to follow from pre-Brexit times are now not open to us. So I think it's going to be very important that the UK invests further putting quantum technologies into space. How might we do that? Well, I think there would certainly be the possibility of further CubeSat missions. I think we could have targeted CubeSat missions beyond the ones that are currently in motion that could investigate specific problems. But of course, another option might be to put up a larger satellite which contains multiple quantum payloads, maybe not just communications, but also some imaging and sensing devices and so on. So I think we're at a very interesting point right now where this discussion really needs to be opened up, and we need to start thinking about what should happen next. Because certainly if we're going to have a much larger satellite, then I think it's important to consider who's going to foot the bill for that, because I don't think the price of a satellite, which in itself is not a quantum thing, is going to come out of the future UK National Quantum Technologies Programme funding. I think that satellite cost would have to come from elsewhere. So I think the time is right now for the conversation about where we go next in the UK with quantum in space. So finally, just to conclude, I'd like to thank all of the hub partners. As I said, that our hub is led from the University of York, but we've got about 10 academic partners and numerous industry partners and national laboratory activity contributing as well, particularly in the standards area. So you know, the work I mentioned very briefly today is clearly a big collaboration between all of these partners, and so I'd like to acknowledge everyone's contributions there. And finally, I'll just close off with a slide that gives you some further information for contact details, if that would be helpful. So thanks very much for listening.